Hello viewers, welcome to my channel. I teach Olympiads and AP Physics with Ambarish, and today I'm feeling very excited to bring an original challenge. I really enjoyed writing this challenge for all of you, and I also feel very happy that I've received very few responses correct. In fact, in the community section I did not receive any correct response to this question, and I gave this problem to my students also, and two of my students were able to do this problem, Arnav Jain and Harshal Singh, although they took quite some time for solving. Another student, Pratyush, he got the method right, but then he bungled up the calculation. So I think that's a pretty good challenge that way, based on the response that I received. So without much ado, let me straight away get into the challenge of the day. And here's my original challenge. What's the challenge? See, a very long semi-infinite cylindrical shell of radius r has a uniform surface charge density sigma. Okay, so there's a very long cylindrical shell. Remember, it's a shell and it has got a surface charge density sigma. Okay, a disc shaped cover of mass m which is divided into four sectors as shown in the figure is placed on the top. So on top of the cylindrical shell, which is supposed to be very long for purpose of modeling, we have placed a disc which is divided into four sectors. Okay, so there are two blue sectors and there are two magenta sectors. Okay, the blue sectors have a charge density sigma, whereas the magenta sectors have a charge density of 3 sigma. So this has got 3. So blue ones have got sigma and sigma, and this has got 3 sigma, and this is also 3 sigma. Okay, what should be the minimum value of m? So m is supposed to be the mass of this disk. Okay, so we have to find the minimum possible value of the mass of the disk so that it doesn't fly off. See, because it will receive some repulsive forces from the cylinder, and if the mass is not sufficient, then it can levitate. Okay, or it can go up, right? So what should be the minimum value of the mass of the disk m if the cover is not to fly off? Acceleration to gravity is g. So if you want, you can give it a try. I'll present my solution right away. Let's see. Okay, so before solving this problem, I'll solve an alternate problem, an easier problem, and then I'll try to relate the easier problem to this one. Okay, so we shall first find force on a uniformly charged disk. Instead of dealing with four sectors right away, I'll just uh, find the force on a uniformly charged disk and then use proportionality arguments to get the forces for this kind of an arrangement. Okay, so and then use symmetry and scaling arguments to solve our actual problem. So now let's say I consider a strip of, let's say, angular width d phi. So the linear width becomes r d phi, right? So this is r d phi, and let's say the equivalent linear charge density. So this will behave like a line charge, right? Why I'm breaking into line charges? Because I know the standard results for a line charge, right? So I've converted it to line charge. So what's the equivalent line charge in terms of sigma? So if you consider an L length along this, so the amount of charge on this will be equal to what? So that charge will be sigma into r d phi into L, right? So sigma into area basically, and that can also be written as lambda into L. So lambda into L is sigma into L into r d phi. So we can say equivalently the linear charge density for this strip is sigma r d phi. Okay. So for now, I'll just refer to it as lambda, and later on we'll put it as sigma r d phi. So let's see how we can proceed. So now we know by symmetry the force on the lid is vertical. See, that can be easily seen that everywhere there's a symmetry. Okay, so therefore the net force must be vertically upward. There will be no horizontal components like this. Radial components will obviously cancel out. So I am interested in calculating only the vertical force due to this line, and then I'll integrate over the all lines on the entire curved surface. Okay, so we shall now find the vertical force due to the line charge on the lid. So what's the vertical component of the field? So it's a standard result when you have a line charge. So what's the field formula? That is lambda by 4 pi epsilon naught in the vertical direction at the end point, and also the horizontal field, but I'm not interested in the horizontal field, right? So the vertical field is lambda by 4 pi epsilon naught r at a distance r. This is a standard result. You know that you have a result in terms of cos alpha and cos beta, where alpha and beta are the angles on the extremities. So I'm using that result straight away. So that's the field at a distance r. Okay, and I'm going to use this result. This is y component of field, right? And I wanted only y component. Now let us look at the lid from the top view. So this is the top view of the lid, and what I'm doing, I'm considering an element of the lid, the uniformly charged lid, right? Right now I'm not dealing with the non-uniform charge density that we have in original problem. So if I have a uniformly charged disk, I'm considering an element centered on this lambda. Okay, so I have drawn an arc which is centered on this line charge, and r and r plus dr. So this is the element of the disk that I am considering. Okay, you also consider this type of element while finding potential at the periphery of a disk, uniformly charged disk. So same kind of element I am finding out here. So idea is to find the force on this and integrate this to find the force on the entire disk, and then we'll do integration over the entire all such lambda all such these line charge. Okay, so let us consider the vertical force and arc element of radius r and thickness dr. We are finding the vertical force. So what's the force? So you know that force is simply field into charge, and charge will be sigma into dA. Okay, so suppose this charge density also sigma, so sigma into dA is the force. So how much is that? So field was lambda by 4 pi epsilon naught r, as we saw just now. And then what's the charge? So charge is charge density into area of this arc element. And what is the area? See, the curves, this length is simply r into 2 theta. So 2r theta, and the thickness is dr. So area becomes 2r theta into dr. So I hope that is clear. And if you simplify this, and r will go off with r, then 2 will cancel one of 4 factor, and this is what you get. Okay. And now if I integrate this from r varying from 0 to 2r, see, the first element will be here and the last element will be at 2r. So I need to integrate this from r varying from 0 to 2r. But the thing is, theta is also varying with the element. You see, here this is theta, and again, if you have an arc like this, this is theta. So what's happening to theta? So here you can see theta at the very initial moment, the theta is equal to pi by 2, and as you are proceeding further, theta is becoming lesser and lesser and lesser, and finally theta goes to 0. So theta is going from pi by 2 to 0 at the last element, right, as small r varies from 0 to 2r. Okay, so here r varies from 0 to 2r, and correspondingly theta varies from pi by 2 to 0. And I need to convert whole thing into single variable. So either I should convert everything to r, or I should convert everything to theta. So I find it more convenient to convert everything to theta. So what I can see from the geometry, you see, this r, this is capital R is the circle radius, this is also circle radius. So this blue triangle that I have just now drawn is an isosceles triangle, and this is your small r, this side is small r, and this you can readily see is this is r cos theta plus r cos theta, that is 2r cos theta, right? So small r is 2r cos theta, 2 capital R cos theta, and therefore I can say dr is nothing but minus 2r sin theta d theta, simple differentiating with respect to theta. And now my integration is ready. I just need to substitute dr. See, this is what I was supposed to find out, and I can now substitute dr directly. So if you substitute dr as minus 2r sin theta d theta and integrate from pi by 2 to 0, you get the force due to that line charge that I'm calling as F sub lambda. That is because of that small line charge, which itself is an elemental force, right? So this is an infinitesimal quantity because lambda has got an infinitesimal, right? So lambda sigma r upon pi epsilon naught. Now this is just the y component of the force due to the considered elemental strip, with lambda corresponding to lambda being equal to sigma r d phi, right? Okay, now and this was the equation number 1. Okay, so now I am using this condition in equation 5. This is your equation 5, so I'm just putting this over here. So lambda is sigma r d phi, and this transforms this to just put sigma r d phi instead of lambda and simplify. That's what you get. And now you integrate it over the entire circle. So phi varying from 0 to 2 pi, right? So you integrate this once again to get the force due to all such strip elements, and phi varying from 0 to 2 pi, this gives you force as 2 sigma square r square upon epsilon. So now remember, this is not our required force. This is the force in case the entire disk has a uniform charge density sigma. Okay, now the same disk, suppose I divide into 4 sectors. So if this is the total force F, then each of these sectors will be having a force of F by 4 by symmetry, right? F by 4, F by 4, F by 4, F by 4, because same charge density is there on all the 4 sectors. So this is the derived case, but now I want to transform it into our actual case. So in our actual case, this blue sector again has the same charge density sigma, but this has got 3 sigma instead of sigma. So in this case, suppose this force was F by 4, then this will get scaled up by a factor of 3 and this force will become 3f by 4, right? Similarly, this force from f by 4 will go to 3f by 4 and these two will remain f by 4, f by 4. So now I can add up all these four forces to get the force for the actual case. So that is f by 4 plus f by 4 plus 3f by 4 plus 3f by 4. That is 2f, right? So that's what I've written. Now if F is the total force on the uniformly charged disk, then by symmetry each sector will experience F by 4. Now for our original geometry, these forces need to be scaled in proportion to the charge density. So required forces, F on the lid is F by 4 plus 3F by 4 plus F by 4 plus 3F by 4, that is 2F. And we already know the value of F, you substitute here and this is what you get, 4 sigma square r square by epsilon naught. Okay, so this is the electrostatic repulsive force, but we wanted the value of mass of the lid. Now it's pretty simple, you can do the vertical force balance. So and mg should be greater than the repulsive force. Okay, then only lid can stay there, otherwise it will levitate and lift off. Okay, so mg is greater than this, so take g over here, so mass is greater than this, but we are asked the minimum mass, so minimum mass is simply this value itself. So minimum mass of the lid is 4 sigma square r square by epsilon naught g. So that was my problem, and I really enjoyed writing this challenge, and I hope you also enjoyed solving this challenge and looking at the video solution analysis of this. And my students also, I'm giving the feedback. I mean, I got the feedback, they really appreciated this challenge, and I'm sure you also would appreciate it as much. So in case you liked my video, please do give it a thumbs up, and please share this video as much as possible with your friends through WhatsApp, Telegram, Discord, or whatever medium you use for networking with students, fellow students preparing for IIT, JEE or Olympiads. And most importantly, if you're not already subscribed to my channel, please do subscribe to my channel, because that's what keeps me motivated to do a new video every day. And thanks a lot for watching this video. Thank you so much, and I'll see you in the next video. And as always, God bless you all. Thank you.